This is a nice story that appeared in Science just a few weeks ago. And where am I here? Okay, so June 2025, and I'm recording this in September, so a couple of months ago. This is about what the cities need for planning for the future of their water supply, wastewater treatment, flood management, etc. So it says hazy futures, protecting the local impacts of global warming is a stubborn challenge, but cities need answers fast. So this is focused, kind of built around the city of Austin in Texas, which is a nice contrast because Austin is, in the US you think of red states and blue states, and red states are Republican leaning and blue states are Democrat leaning, Democratic kind of entities in elections, and then you have other shades of color where you have mixes. So in 2011 a record drought dried up reservoirs in central Texas, raising fears that global warming will further stress local water supplies. So there is a river called Texas, Colorado, which is, a source of water for the city of Austin, which is the focus here. And Texas is a semi-arid region overall, and has been, sits in the armpit of the Gulf of Mexico, which is a very warm water body. And then there are issues of cyclones and tornadoes, droughts, and so on. And it's generally a red state which has a lot of climate change issues, let's say. Okay, I won't read all the details, but it's about taking perspectives from various scientists and administrators to try to say what the science is offering and whether that's good enough or not. So you have the global projections with technical lingo, jargon like CMIP5, CMIP6, coupled model intercomparison project under the IPCC, Intergovernmental Panel on Climate Change, which provides the regular assessments of all the literature and model simulations to say where we are headed, and it often goes beyond 2100, and there's a lot of debate about whether it's reliable. And the general idea is that in the first couple of decades, internal variability or model uncertainties dominate the spread in the projections, and after that the scenarios, we assume, tend to dominate the uncertainties in the projections for temperature, and then everything else from rainfall to extreme events, cyclones, and so on. But here the approaches of downscaling them to any scale, like a city scale, has been about either statistical approaches, the older one basically aggregated the available data into a grid scale of the models and then did some comparison and then projection and then disaggregated back. And so there are approaches which are purely statistical. There have been downscaling models used as well, and that have other issues with boundary conditions. And now AI is becoming more and more popular, and people are arguing we don't even need the models, we just do AI. Okay, I mean, we don't need regional models and so on. So let's read a little bit. Austin was apparently designed well in terms of its wastewater treatment, but now it's facing droughts and then has an uncertain future just by looking at the future projections, because some models say it will be a very dry future and some models say it may be wet with extreme events and so on. So they have to plan to adjust these things. So what they are doing is Austin, based on a climate study that predicts more severe droughts in Austin's future, the city is planning by 2050 to increase the amount of reused water by more than 10 times as part of a $1 billion expansion of the plant. That program is going to grow exponentially, said one of the people asked, Weber. But you get the idea that there may be some no-regret decisions, recycling wastewater for certain uses. It doesn't matter what the climate does, this may be a good thing for arid, semi-arid states. So, like many cities around the world, Austin is now facing questions about how to build and adapt for changing climate, and there is little agreement on how best to convert global models into local projections. Global models do very well, let's say, for global projections. So global warming over the 20th century has been fairly reliably been reproduced by these models, given the greenhouse gas increases and other things like volcanic eruptions, land use changes, urbanization, deforestation, etc. But the scales of temperatures at which they are reliable beyond the global scale is at, let's say, a continental scale. It will most definitely be not very reliable at the Austin scale or any other city scale. So that's where the problems are in terms of what heat waves may do in the future, what mean rainfall or extreme events may do in the future, and if you want to produce such information from these models, what is the best way to do that. So that's kind of the debate in this article. So right now it's a mess. Different projections, different downscaling methods of projections lead to different results. So Alex Hall from UCLA says it's a mess right now, and there are many people working on this. Ben Kerdman from Miami has been funded to compare downscaling methods, and basically he wants to produce somehow reliable downscaled products for projections. You want to convert them to risks for flood and so on, but you cannot directly downscale risks. You have to downscale the climate component, the hazards, and then do vulnerability exposure, etc., to produce risk maps for the future. So it's quite a complicated business. Okay. Despite nailing the overall pace and intensity of global warming, models did not predict the more frequent heat waves that are plaguing Europe. There are many biases. Tiffany Shaw points out, there are papers pointing out so many biases. On the one hand, you will have papers talking about what the future will look like for heat waves over India and floods and droughts over India, wildfires in the western US, or stream flows in Europe and so on. But on the other hand, if you just compare with reality, those models have a lot of problems, biases, uncertainties, but the decisions are very urgent. Austin cannot wait to see whether the models will get it right. It has to make decisions at various time scales. Okay, so how to get this information reliably? So located in the dry Texas Hill Country, Austin has always depended on Colorado River, not the main one, but the Texas Colorado River. And there are various numbers about how things have evolved over time. The city itself has grown tremendously, obviously. It's now a technology hotspot, educational center, and generally kind of an oasis in the south in terms of a nice city life, let's say. Okay, so reservoirs made Austin more resilient, but not impregnably so. From 2008 to 2016, the city suffered its worst drought since the 1950s. So there are people like Marisa Flores Gonzalez, who leads water resources planning at Austin Water, the city's utility. When you are in the middle of a drought that's very severe, you don't know where the bottom is. So you don't, if the drought lasts for multiple years, the projections are not good enough to tell you when it may end, and that whether that can be used to help plan the water, the little precious water that is left, and so on. Okay. So they have been working on solutions. We are a land of extremes, she says. We have to be prepared, obviously, but the question is, in which direction? Do you prepare for a wet future with long spells of dryness, or is it going to be just dry all the time, or is it going to be very wet, and so on? So Flores Gonzalez had studied the Texas landscape from an early age, and then she moved after studying at the University of Texas at Austin. She pursued an English degree. I was going to be the next great Mexican-American writer, she says. Then in 2008, recession hit and she switched to geography. So she got into this business rather serendipitously, but nonetheless, she's now waiting to play a bigger role. Projections that ended up in 2018 report that was produced weren't surprising. Austin would have more dry days, and on days when it did rain, it would rain more, reflecting the ability of warmer air, to hold more water. Atmosphere is like a sponge. If you warm it, it soaks up more water, and then if you push on it like instabilities, then it pours more in some places and much less in other places, and so on. So the river is supposed to be 30% dry or lower in its annual flows in a couple of decades. Okay, but out of the 20 models they looked at, many also were projecting a very wet future. So should it really prepare to be wetter also, in addition to dealing with the drier outcomes with global warming? Marisa Flores Gonzalez here led the efforts in Austin, Texas to use climate models to guide the city's development plans, which include boosting the reuse of treated water from its Walnut Creek sewage plant. So cities produce obviously lots of solid waste, wet waste, wastewater, and always a problem, but recycling wastewater, as I said, is a no regret decision if it could be done. There is always a return on investment, cost benefit analysis needed, but externalities like dealing with water shortage cannot be directly accounted for in just converting wastewater into reusable water, right? When you hear the phrase climate model, people think researchers have created a silicon simulacrum of the planet, but obviously models have lots of biases, but also the information they provide is at about 100-kilometer range. It may get down to 50-kilometer in the next assessment coming out in 2028, but nonetheless you are talking about Austin, which is much smaller, and then you're talking about Austin's water resources, which are even smaller. Then Texas Colorado River has its catchment area, so you need information there as well, and so on. So the big picture, models get a lot right, but the basic physics is sound, but they are biased or differ from nature in many ways. They are amazing in the sense you give it the energy at the top of the atmosphere, and then they do everything. El Nino, La Nina, and the decadal variability, and the Texas warming, Gulf of Mexico warming, and so on. But they are all at the scale that, for various physics reasons, are not reliable at very small scale, and temperature is done much better than rainfall. We have discussed this elsewhere. I won't go into these here. So Tiffany Shaw comments on how the models suffer from these kinds of issues, and they have written about the biases, and so obviously there are many issues. Models missed the more frequent occurrence of stalled high-pressure systems over Greenland, which bring sunny days and rapid ice melt. And once you start melting the top of the glacier and water ponds form, they reduce the reflectivity of the sunlight and absorb more energy, and then the melting accelerates, and then those meltwaters drill into the glaciers and create so-called moulins, which can go all the way to the bottom and begin to lubricate the slip and slide of the glaciers down the slopes into the ocean, and so on. So given models' limitations, many climate scientists eschew regional projections and think the even harder task of making hyperlocal predictions is a fool's errand. Well, many advances have been made already in terms of using AI and data and models to produce reliable hyperlocal predictions. So it's not a complete wash, but obviously it depends on data. Lots of data is needed to do it reliably, and even if you have a lot of data, sometimes the AI may not have seen jumps that may occur, regime shifts, or emergent properties in this intrinsically nonlinear system. So there are always issues, but still we are making progress on that for sure. And there are other people interviewed here, like Arup Ganguly, who has collaborated with people like Subhi Bimal Ghosh and his student Vikram Shandell on looking at the problems with downscaling. They looked at one called bias correction and something SD. BCSD, spatial disaggregation, bias correction and spatial disaggregation, and argue that that approach actually begins to misrepresent the physics. So that's kind of scary when you take something and downscale it and then it becomes dynamically inconsistent, and that's not very useful. So one way to do this is downscaling and bias correction as it is known, but such models can capture many things well, but then they also produce other problems. Okay, it's also, you cannot take a 100-kilometer model down to few meters or 1 kilometer unless you have enough data-based information which will allow you to do that. So those are always the details. Here is a figure, unwelcome surprises. Climate models are good at the big picture of global warming, but at a regional level they have blind spots. With decades of observations in hand, researchers can now identify local climate trends the models failed to predict. In other words, the predictions are obviously tested where the prediction gets to be tested next day, because if it didn't get it right, then you know immediately. Seasonal forecasts can happen the same way. El Nino forecast, if you miss it this year, you have to wait approximately 4 years for the next prediction and so on. But with global projections, longer term integrations made, let's say from the 1997 projections into 2020, now we get to test it and see how models are doing things wrong, not just in historical simulations but in the previous projections. So that gives you ideas on how temperature, rainfall, humidity and winds are being missed. So winds here, unforeseen shifts in wind patterns have led to more stalled sunny weather over Greenland. We'll see a figure later on. They have also strengthened the jet stream over the Atlantic Ocean and intensified storm tracks over the Southern Ocean. So the discussion of the jet stream, whether it's become more meandering because of Arctic warming or not, went on for a while, but now there seems to be a consensus that in fact the warming patterns have created the jet stream to intensify and become more wobbly, which means it brings extreme weather on the mid-latitudes in the northern hemisphere and some excursions into the monsoon domains and so on as well. Okay, so computationally cheaper method was engineered or pioneered by Andy Wood, hydrologist at the National Center for Atmospheric Research. He averaged the data into a spatial scale of the models and then disaggregated, as I said, but those have issues by now, as publications have shown. So here is Aurup Ganguly from the Woods and others laid out. So that's the Woods paper in Environmental Research Letters, which talks about problems with downscaling. We still have no real confidence to determine that one downscaling method is better than another, Andy Wood says, and Ben Kurtman has a project to compare the methods, as I said before. And Aurup Ganguly is here. He's a climate scientist who was involved in this study. All the best science that goes into building these Earth system models was rendered meaningless when they did the downscaling, and the real climate data and the random noise couldn't be really separated. So I'm being brief about it, but you get the point. The point is you cannot just assume that you are going to be able to downscale global projections to a city scale or even higher resolutions and get reliable decision-making information. So we have to really figure this out correctly. Wood makes other comments here. Wood also wonders whether projections from global models, however coarse and unreliable, are good enough for practical purposes. Tim Palmer has talked about this. Tim Palmer and colleagues from the European centers argue for 1 kilometer scale global models because they say any coarser resolution, even 5 kilometer, may never give reliable information for making decisions. And then there's the issue of how to manage such a high resolution model in terms of computational resources. The output that comes out will be so massive that you will need to use methods like AI to diagnose the information out of them to produce bits of information that water managers can use, for example. Okay, so you can go back to the Austin Water Forward report, and they basically went to climate researchers at UT Austin who did it slightly differently. They picked models that did best over Texas and Austin and produced projections from those models. There are various details that I'll skip, and they produced what appears to be more reliable projections that Austin could use. So Yang and Tabassum from UT Austin made several changes for the approach they used. So knowing the different biases that existed, they didn't treat every climate model as equally since they don't know what the strengths and weaknesses are. Okay, so they converted the output into regional forecast using standard downscaling and bias correction method, but because the models tracked the region so well, Yang says the corrections were relatively minor. So when you have a large selection of models, it's tempting to look for models that are doing well over Austin, but that comparison typically happens for the historic period. Does that guarantee that they're also going to be reliable for the future? Not necessarily, but you keep coming back to the same thing, that you need to make decisions, so you need to do the best you can to find reliable projections. So these are the best approaches right now. Okay, so extreme flows were less prevalent in this round than in the last one in terms of downscaled projections. So they have to now plan basically for all this. After integrating these projections with others such as population growth, the team found that in half of the scenarios considered, the city would begin to run out of water in 2070. How to plan for that? That's a completely different set of issues in terms of finances and longevity of the solutions and the flexibility you will need in the solutions in terms of being able to deal with heavy extreme rainfall maybe and wetter future versus a drier future. Okay, so the new water forward report approved by the Austin City Council late last year includes strategies to forestall that future. So it's about managing the unavoidable and avoiding the unmanageable as best as possible. So future is drier and riskier but still livable is what the last report said. So going forward with Austin, there are other ideas that do this over and over again, and you can ultimately assess how well they work. So this is Ben Kurtman's project of pitting different downscaling techniques against each other and applying them to different climate models and see how the results diverge. Berkeley Earth is also offering some solution where they look at 40 global climate models in each region of the world and find the ones that best match historical observations. So, as I said, this is the best we can do right now. One model will not do well over all the regions, but multiple models do well in some regions, and you select those and hope that the current performance is an indicator of their future performance. Okay, so zooming into the future, global climate models which divide the planet up into coarser grid cells can project the world's fate under global warming, but applying these results at the scale of a city or farm is a persistent challenge. For example, a GCM might predict average monthly rainfall for a grid cell decades into the future, and there are some ideas on how you may be right and yet you may be wrong. Climatology may persist, but the distribution in space and time might change within that grid. GCM grid cells now tend to be 100 kilometer by 100 kilometer by 100 kilometer in latitude and longitude, but even a 100 kilometer grid cell is too coarse to make predictions at that the local officials want and can use. Two main methods are used to translate GCMs into local areas, and both are fraught with problems. So local area can be 10 kilometer by 10 kilometer in terms of needed climate predictions, but It depends. For future decisions at decades and longer, you need this scale. But if you want to manage heat waves, it'll be a very different scale. But that downscaling problem is also slightly different than downscaling projections. What are the methods? Statistical downscaling by comparing GCM results for the past with weather station measurements. The model results can be adapted to a local region. So predicted climate metrics such as temperature, prediction for coarse GCM grid cell here, weather observations are averaged across the GCM cell to make a direct comparison, because you may have weather stations in a grid cell or multiple weather stations, so you have to make fair comparisons. Uncorrected prediction into the future may go this way. This is the past, this is the present, this is the future. So here correction of the model into the future based on the past biases and uncertainties. There are various details. The mismatch between observations and past model predictions is used to adjust future projections. Grid scale predictions are disaggregated to match the resolution of weather observations. So this is a local area prediction. As we said, bias correction and spatial disaggregation can have serious issues, as Arup Ganguly and the paper with his colleagues pointed out. Weaknesses: assumes correlation between historic weather and GCM do not change in the future. It's an emergent nonlinear system, so this is inherently a shaky assumption. Different statistical methods produce different results. So it's not just the correlation assumption, but the methods themselves, even in the past, can be producing different results. Regional climate models: GCM is on a 100-kilometer scale. Regional climate model can be much finer. There are limitations into how fine they can get, because there are certain assumptions on turbulence and so on that may not work if you go beyond or above about half a kilometer. You cannot run regional climate model at 10-meter resolution in many cases, for example. So local area within the RCM grid, regional climate model, local results from the RCM must still be bias corrected using historical observations. So what are the weaknesses here? These inherit GCM's biases because they are driving the information at the boundaries, and require supercomputers, making it infeasible for many users. There are many technical details which I have discussed in the climate modeling course that you can look up. Okay, so that's the Berkeley's approach of taking multiple models, picking them based on their performance at each region across the world, and then doing bias correction, producing downscaled projections, and so on. Other way is to, of course, just run high resolution models. The EU is gung-ho about it, so they are trying to run a 5-kilometer resolution model, but obviously it's a massive task in terms of computations, and they are only out to about 2040. But there are others, Google's AI, so here ECMWF and Google among others have teams looking at how to use such advanced AI. I jumped the AI discussion here, but to entirely replace the downscaling done by high resolution regional climate models. After training on a climate model, Google's AI substitute proved particularly good at capturing compound extremes such as high heat and winds occurring together. It allows us to really sample all the possible states of the atmosphere, says Ignacio Lopez Gomez, who led a Google study published in April in the Proceedings of the National Academy of Sciences. And the limited computation needed to run it could make its power widely available. So AI will be faster and cheaper to run, and if it can be more accurate reliably, then you have a real game changer. And I have recorded this as a separate podcast as well that you can look up. Okay, so basically coming back to Austin, the next 10 years are going to be some of the most important years in Austin's water history, said Flores Gonzalez again. Adaptation can't come soon enough. Several years ago, the city once again plunged into drought, and its bottom is still unknown. Okay, so it's a constantly evolving situation. So this is about Greenland. Although good at projecting global trends, climate models have missed regional phenomena such as an uptick in clear sky weather over Greenland that has exacerbated the melt. And as I said, once the albedo ice feedbacks happen with the melt ponds, you can begin to form serious rivers of meltwater that drill into the glacier and create cascades that are really not very good news at all. Okay, so as I said, I've been brief about this. It's a very nice report that you can go and read, and even though I'm being brief, it's about 30 minutes long, but hopefully it still gets all the main points across. But definitely go and read it if you wish to find out other points made in the report. Okay, see you.